So, we've not got long. My excuse for this talk is, have you come across the phrase regression before? So often applied to curve fitting. Do you know why it's called regression? I'll tell you in under half an hour. And I might tell you a bit of history and computing as we go and things. I'm going to pull us back from talking about LLMs specifically. Just time for afternoon chill out, broad view of things, and you'll learn one thing, why it's called regression. So, regression towards mediocrity. I'm going to define some terms and look at quite a long history. Then we're going to do some mathematics, but you'll be pleased to know I'm not going to put any numbers in this. We're just going to keep an abstract equation that you probably have come across at school. You might have forgotten, and that's fine. And we're going to look at how that is actually a way into understanding a bit more about what all kinds of different neural networks are really up to. And then we're going to think about how to go beyond being mediocre. Just a few little hints and tips for any devs or testers. Are there any devs or testers in the room? A few. Cool. So I'm Fran. I hang out in various places. I will share the slides somewhere at some point, probably via LinkedIn. I'm a member of a little tiny group called ACCU that focus on particularly C++ development stuff. So I edit their magazines. So anyone wants to write an article about dev, testing, techie stuff, get in touch and I can help you get it published. Little plug, little aside. So, now I've wasted several minutes. Let's get to the point. If you think about the history of computers themselves, you might be surprised to learn just how old the idea of machine learning and AI actually is. Several people have got the impression that AI is a current thing that's only just picked up and started happening because using ChatGPT or similar, because it's got the chat interface, it's really easy to use. Daniel mentioned I did a PhD. It was quite a few years ago now, before you could use like TensorFlow and loads of Python models. So I had some neural networks in the machine learning I was doing, and I hand-coded them in C++, which means I understand how they work. So yes, things have changed, but some of this is quite old. I said about defining terms and reminding ourselves why it's called regression. How would you define a computer? If we were playing the game we were playing just before lunch, can you even do that? That's really hard. Go away and think about it. So if you look at history, you see automation going on. And the closest point at which it starts looking really like computers is weaving on a loom. So you've got the same hardware, the same loom, but you can put a different card into the loom, and that'll change which threads gets picked up and which patterns you get out on the curtains or the bedspread or similar. So that idea of not having to have people hand weaving things, being able to control things with instructions, to automate a process, to make it quicker, maybe simpler, dates back to like 1800s or so. Some arguments about whether Jacquard actually invented it or not, which is always the case in history. Maybe you wouldn't really think of that as a computer nowadays, but it's still got that fundamental idea of a machine that will come out of different outputs depending on how it's programmed, if you see the card going in as a program. And you move on from that to some thoughts from Babbage about what could you actually build in terms of a machine. Instead of weaving, perhaps you could drop out numeric tables or similar, in a similar way. And then you end up with a precursor of punch cards to do some calculations in kind of glorified calculators at that point. And by the time the Second World War kicks off, then we start getting things that look even more like the computers we're maybe used to today. I've cheated and haven't defined what a computer is. I think that's a very hard thing to do. But it's about automation and maybe be able to change how a machine behaves by giving it different instructions. It's the best I've got. If we look at some more history, originally we used the word computer to describe people, particularly around the time of the Second World War, but before that as well. Lots of things like the insurance industry and other things, you needed people to crunch numbers, and lots of female graduates from mathematics would sit in a room and manually calculate things. And they were called computers because they were doing computations. And then that gave you a natural move towards the women doing, well, what looked like typing on the new computers during the time of the Second World War and just afterwards. And we called them computers still until we started calling the machines that were replacing them computers. I'm always amused that, certainly in England, all the first programmers were female, and something switched, possibly around the 70s and 80s at some point. But that's another story, and we've only got half an hour. So a computer used to be a person, but we don't think of it like that anymore. So I talked about the Second World War, and I think particularly in England, we tend to think of touring and things going on at Bletchley Park. But actually a guy called Conrad Zuse came out with the first actual programming language, which, like the looms that you put different cards in and get different bedspreads out the other end, programming language lets you program a computer. We all know that, even though only a few of you put your hands up to say you're devs. Now, this is right at the beginning of computing in the 1940s. And he knew that these weren't just calculators. They could do a lot more than that, but people didn't realise. And this is where the AI comes in, right at the beginning of computers. It's obvious when you think about it, and the first few people who were writing computer programs thought this, right? Zeus thought, all right, if I write a program and store it, the program could read itself in, and I could set up some calculations that allow and encourage the program to modify itself, which means that the computer would be programming itself. So that observation was right there, right at the beginning of computers happening. So this AI thing is as old as computers, if not slightly older. Not got time to go into some of the other things about robotics there. Anyone heard of the programming language Lisp? That was deliberately designed to be really simple to parse and easy to self-modify. The reason that exists was in order to write a programming language that could self-modify. So you could kick it off, and then the computer with the code could be out in space, mining for asteroids, for precious metals or other resources we need, and fix itself and change as needed as the environment changed. I mean, that's one type of AI, isn't it? If a program can rewrite itself on the fly as the environment changes. So right back there from the beginning. Where else was AI? Well, before we've got as far as the 40s, people have been trying to see, could you theoretically get a machine to enumerate all the maths that there was? Because it seemed like some mathematics follows from some other mathematics, so perhaps you could enumerate every true theorem. And a guy called Hilbert tried to do that. We hit a roadblock. Kurt Gödel pointed out that you've got this inherent inconsistency. And I can talk to you about Gödel's incompleteness theorems properly, but not in half an hour. You come across Gödel's incompleteness theorems before. Okay, executive summary. What he's saying is, if you're trying to list every possible part of mathematics, or every possible computer program, you're either going to end up with two contradictory things, or you're going to miss something out. And you can prove that with some theoretical mathematics. And to me, that's kind of quite hopeful. That means a machine won't be able to enumerate everything that's true in mathematics and other realms. It will always miss something out, or it'll contradict itself. And I think that gives us the possibility of some creativity still, which is nice. But it does mean there's some limits around what's possible with computers. It doesn't mean they can't program themselves, and it doesn't mean we can't have some kind of AI. But there's a hint in there in a bigger, wider history that there are some theoretical limits on what's possible with pure computation. Again, that opens up a bigger question. And I still haven't even defined what a computer is for you, so I'm not helping. Perhaps all you're going to come away with this afternoon is some questions, and at least an understanding. There's history we've forgotten, and there's lots of terms we haven't defined clearly. Yeah, after this Church-Turing thesis, which is that if you build various different machines, in effect, they're all capable of calculating the same thing, and they've still got this same hard limit from Gödel saying you can't list every possible program. You can't list all of mathematics. There's some things you cannot do, and you can prove you cannot do that. But they can simulate some amount of formal reasoning. They won't be able to think of all the things for you, but they can look like they're reasoning. And that leads people to start using words like machine learning. That dates back to 1954. I think it became quite a current word in the last 10 years or so. People hadn't tended to hear of it before that. That's a really old term. A guy, Arthur Samuel, thought, I've got a computer, I wonder if I can teach it to play checkers or drafts, depending on what you call it, just a simple board game. A lot of the history of computers is people playing around with games. I don't know about the rest of you, but that's what I like doing with my computer, because games are fun. Shortly after that, John McCarthy set up a workshop which he describes as discussing artificial intelligence, and that's where we've taken that term from, just the name of a little workshop that happened. Back in the 50s, this is nearly as old as computers. Haven't defined what a computer is. I'm not going to define what AI is. I don't think we can define it properly. It's certainly not just what's happening at the moment. All of this goes back to the beginning of computers. Something called cellular automata. Anyone heard of Conway's Game of Life? If you haven't, look it up. It's just got some very simple rules for squares on a grid. They're either coloured in, which symbolises something's alive there, or they're not coloured in, something's not alive. With very few simple rules, you get these really complex patterns emerging. Now, they had been designed with the idea of actually having little simple robot agents with a tiny number of rules in that you could send off onto asteroids to do mining that would bring back useful chemicals for us, that would also be able to develop complicated behaviours, which might be part of AI, and fix themselves if something went wrong, something that could be autonomous. And cellular, just because they were going to be small. And you can use them to solve problems, and I could talk to you about that as well, but that counts as part of AI. You can build machines that play games. I talked about checkers or drafts. We've seen computers learn to play and win at chess and Go. And there's aside things with reinforcement learning, with computers learning how to play old arcade games like Pac-Man and win at them. But whether that's useful or not, don't know. But it looks like the machine's learning something. Whether it's actually learning or not, I don't know. How do you know whether you've actually learnt something or not? You might be able to do something you couldn't do before, but perhaps you're just parroting things or remembering things. Perhaps that's what learning's about anyway. Throwing out questions. No answers here, apart from why it's called regression. So I better keep an eye on the time. You see, broader things. I mean, neural networks have got talked about. Expert systems used to be a big thing where a human would encode some data in a database. And you could do that for like medical diagnoses. And you might have had that if you've gone to one of the NHS online websites. It'll give you a series of questions, say, have you got a temperature, this, that, and the other, and then go to the end and say, dial 999 immediately, or have a hot cup of tea. That's information encoded in some kind of flow diagram. So that's something we still use, and back in the 60s and 70s, that was hailed as, this is the future of AI. It's a collaboration of information from experts coded up in a computer. Whether that's artificial intelligence or not, it's certainly automating something. Now we see neural networks and natural language processing, and there's been talk today about solving specific tasks like playing drafts or chess, or encoding data for a medical doctor so that you could self-assess your own problems. And that's not the same as the idea of general intelligence and learning. But I think it's quite hard to define intelligence anyway. But certainly the AI we've seen all through since the beginning of computers hasn't got to a point where it appears to be able to self-learn and take on board new tasks. But some people don't do that very well either. Don't know. Not defined terms for you. A lot of that's about software stuff. And there's a hint from the cellular automata about robots and hardware. And that's something we're not seeing talked about much whilst people are talking about LLMs. There's lots of history around autonomous robots that puts a different spin on what intelligence means. Again, that's a broader discussion. And there are robots out there that like go in and find survivors when a building's collapsed. You can remote control these things to sense, but you can actually leave them to go and sense. So there's some innovations in hardware as well as software. We do have lots of recurring themes, though, whether it's the hardware or the software or playing games or medical diagnoses. We've forgotten history. Has anyone heard of Zeus before? No. It's a thing. And we've forgotten about the original coders being female. We've forgotten our history. I think it's quite good to take a step back and remind ourselves every now and then. Sometimes you might spot a direction that we've forgotten about that might be fruitful for further research. And we have seen throughout history things being overpromised, particularly around AI and computing, and then under-delivering and people losing interest. I wonder if that's likely to happen with the LLMs at the moment. If it does, don't lose heart. Just remember, these things cycle round. Things get trendy and then get less popular. Things bounce up and down. There's been lots of bias baked into computing and AI as well. But that happens more generally, so that should be no surprise. If nothing else, we can learn by just taking a step back, and that's partly why we're here, whether it's this specific talk to take a step back and have a think, or this whole conference to give yourself space to think about things. If the machines aren't intelligent, it isn't actually AI or machine learning, that's cool. They might be able to help us out with some stuff, and we might learn as we think about it. Is AI snake oil? Sometimes sold like that. But no, right? AI and computing has done lots of cool and important things. We've automated loads of stuff that's tedious and boring. Just back to the looms again and things. Automation can make things better. Labelling photos. I'm not right saying whether it's a cat or a dog. Fine. But we can detect tumours. sometimes, not always, better than the human eye looking at scans. And other things like spotting, like heat sensors, people under rubble in buildings and things. So computers can make things better for us. And translations between natural languages, I'm not very good at any languages other than English, but I can now look things up and communicate better with people who don't speak English. There's just so many cool things that have happened. So don't be disappointed or downhearted if we have overpromised on some things. Just, there've been some great victories, and there'll be more. There will. Now, I promised you were going to leave this talk knowing why it was called regression. If you've got some data, for example, people's heights, whether that's against their weights or ages, or maybe their parents' heights, we'll get there in a moment, you can just keep all the data and look things up, but then you might have someone who's in between. And if one of the values is parents' average height, you're going to have to find where they would have been in the table and guess a part-way point. That's called interpolation. What you can do is you can, instead of just saving all the data, you can go, well, if I squint, it looks like it's kind of a straight line. I could put through that. Don't know if you remember drawing straight lines at school. You can use the equation saying the y value, so that's the height, how high up we go on our graph, is some number, some magic number, the gradient, times the x value, plus some constant. And you can describe any straight line with that equation. So, if you've got some data points, you can figure out what value to give M and what value to give C to make it as close as possible to all the data points. And that's giving you a way of summarising things. You can measure how good the fit is, which gives you ideas of correlation. That doesn't mean that one value, like the parent's height, is directly causing the child's height. It might be related. It gives you a measure of how close you've got to the points. That's fitting a curve to some data points. Doesn't have to be a straight line, but the simplest mathematical one is just a straight line. The maths gets more complicated as you try other shapes. So, give them some points. Knowing I want to come out with y equals mx plus c, I need to work out m and c. We could just guess values for them and see how far off you were for each point and add up how far off you are, and then you've got an error value. And you want the error to be as small as possible to make them as close as possible. Okay, let's try a slightly smaller number for m. Have I got better or not? You could guess. You could actually do some mathematics to figure this out. But the basic idea here is give them some points, try and draw a straight line through them. And that gives us an equation. And we're just trying to fill two numbers in there. If you remember one thing from this, aside from why it's called regression, these four graphs, if I draw the line of best fit that I work out mathematically, or by that random left a bit, right a bit, make m bigger, make m smaller, make c bigger, make c smaller. That line is the best fitting line for those four data points. Who thinks that's a sensible way of summarising the data? It kind of works for the one on the top left, but you've got an obvious curve. Sometimes straight line's not best. You've got another one that's got a line, but it's got this one outlier. The shape of the model you come out with is going to drive you towards possibly some wrong conclusions. There's a site called Stack Overflow, which gives you some answers to some technical languages. If you start drawing straight line graphs of things, you might come to some wacky conclusions. Why is this linear curve fitting sometimes called regression? There's a guy called Francis Galton who published a paper. He was very pleased with himself. He drew a graph of the median height between mum and dad and the child's height. If the child got taller, the parents were probably shorter, and vice versa. And he was measuring lots of farmers and farm labourers, and he observed that they regressed towards the mediocrity. Here was meaning the median height of mum and dad. So it's like all these poor farm labourers are tending to stay short, unlike us well-educated people who tend to be taller. So there's a degree of classism there. And the regression's not a nice word. It's saying going backwards, staying short. So that's why it's called regression, because of this Galton guy. But by observing this and coming out with some other statistics, he found some useful things too. He hung out with loads of other founding fathers of statistics, that Fisher as well, there's a line here towards eugenics and some horrible things. But the mathematics is still right, but don't fit a straight line if your points are in a curve. Right, let's zoom through and see what this has got to do with anything else. Like I said, Galton did say some things. Sometimes the averages do give you better ideas. So he's not wrong. He was just biased. The early neural networks are trying to do the same thing. They're just not using a straight line. So if we've started with y equals mx plus c, now instead of having one x going in, we might have lots of x's. And the game is to work out what the m and c are. But rather than just fitting a straight line to things, we're chucking some other function that's not a straight line, and that lets us fit loads of different shapes. But they're still doing the same thing, trying to find out the value of m, the weights, one of the parameters, and the value of c, which is ironically called a bias in a neural network. Insert other talk here. You can do different shapes of neural networks. Basic one, bottom left. If you want a deep neural network, you just add extra bits in the middle, which means you're doing more multiplying and adding up, so you need to find out more values for m and c, so it takes more computation. You can do things like just look at the first few inputs, then the next few inputs, and roll over things, and that gives you a convolutional neural network. All of these things are just different shapes, but under the hood, always mx plus c with a non-linear function. So, just if you are into dev stuff, that y equals mx plus c might be familiar from school. You can get the hang of some of this. Don't forget what you already know about DevOps and the rest. I'm going to zoom through because we're running out. You do tend to knock together a spreadsheet or a Jupyter notebook for some machine learning stuff. But other people might need to use your notebooks. Put things in version control, test things, talk to each other. And let's see if we're on the same page. How good is your line of best fit? Yeah, okay, but it looks to me like it's a curve rather than a straight line. Let's talk. Let's learn the same lingo as each other. Let's remember some of the history. Let's remember the good things that have worked, and more will work too. So do what you love doing, but if you're a dev or a product owner or just interested, talk to someone else. Get a broader perspective on things. So let's dismiss being mediocre. Let's never mention regression again. It's curve fitting, much better. Learn some things you don't know, and hopefully you're learning things here at this conference. I've still got loads more to learn about this. It doesn't matter if you can't do the maths yourself. If you're interested, find it out. It's not as hard as you think, actually. If you've done some maths up to A level, you will be able to follow it. We're in this together. If you're testing things, be aware that a lot of the AI and machine learning stuff's got randomness in. So you do the same thing twice and you might not get the same outputs. You need a discussion about what you're trying to test there. and chat to me over a coffee, because I've got some pointers on that one. And that's it, really. We're in this together. Let's help each other out and learn from history and each other. Thank you for listening.